Before we do the comparison test, I want to make sure that you understand what we have done so far. So we did the p-test, which says if you add 1 over n to the p, this thing converges if p is bigger than 1, and it diverges if p is 1 or less. So, and specific examples, which is important for you to know, is that if you have summation of 1 over n squared, does this converge? Does this converge? 1 over n squared. Summation.
Bigger than 1, so it diverges.
This.
It does converge.
It converges because p is
sorry.
2. Yeah. P is 2, right? P is 2, so 2 is greater than 1, so it diverges. No, converges. Okay. Whereas if you had summation of n equals to 1 to infinity 1 over square root of n, what about this one? Converges?
Diverges.
Diverges because square root of n is same as n to the 1/2 power, right? So this is the case where p is 1/2, so this diverges. And then what's right in between is something like n equals to 1 to infinity 1 over n. And we talked about this last time, why this diverges. Well, I showed you that this diverges by using the integral test. I don't want to restate the integral test, but it's just roughly, if you change n as x, so if you integrate 1 over x from integral from 1 through infinity, if that converges, this will converge. If it diverges, this will diverge, and it happened to diverge, so that this diverged. Okay. And then we also did geometric series. The formula for the geometric series was a over 1 minus r. It only converges to that value if the common ratio is between -1 and 1. We also did the alternating series. Alternating series means the signs go plus minus, right? And it will converge if the limit of individual sequence is 0 and the absolute values of the sequences is decreasing. And then we also did this where if the limit of the sequence is not equal to 0, then there's no hope for the summation to converge. This last one's called the nth term test, or test for divergence. I tend to like the word test for divergence because this test can only be used for testing whether something diverges. You can't use it for converging tests. So back to here. So what this is saying is that if the limit of the individual sequence goes to 0, then you don't know if the summation will diverge or converge. And a good example is the p-series. So not only p-series will be an important reference point for your other tests, but just understanding the way that the series diverges and converges will give you a good intuition of what's happening. So here's something to think about. 1 over n squared and 1 over n. As sequences, which go to 0 faster? 1 over n squared, top one, because if you have 100 squared, that's like 10,000. 1 over 10,000 is much smaller than 1 over 100. Right? So this goes to 0 much faster. And you have to think about this image where you're jumping, and the step size of the jumps are these things that you're adding. And they're both decreasing to 0, but somehow, if you're adding 1 over n, the step sizes do decrease, but they still manage to add up to infinity. It was a little counterintuitive, but it was possible, right? That's what we spent time on trying to prove ourselves that's true, right? On the other hand, this will be decreasing much faster, so it becomes 0 much quicker, so that it loses its energy quickly and it fails to go beyond certain points. So in fact, if you add this, you'll see that the total sum will be less than 2. It stops somewhere before reaching 2. Whereas this one, can definitely go beyond 2 and even 3 or even 1,000 if you add enough terms. So that's the big difference. And so you should kind of have this intuition about the speed where individual terms are going to 0. Some terms go to 0 really quickly, some terms go to 0 relatively slowly. And if it's reaching 0 slowly, then the summation will become infinity. And this one, if you think about 1 over square root of n, now let's compare these two. Which one goes to 0 faster? The bottom one, because if the denominator is smaller than the entire fraction is bigger, right? Denominator becoming smaller means that the fraction is bigger. So this is a bigger jump than this one. And because this thing adds up to infinity, if you add something that's smaller, that's bigger than this one, of course we'll have to go to infinity as well, right? So another thing that you should think about is that if this diverges to infinity, then this should also diverge to infinity because this is bigger than this. Okay? And that idea is basically the comparison test. So let me write down the statement of the comparison test. So first, if an is bigger than bn and summation of bn is infinity. Well, I wrote it as starting from 1, but all these tests you can start at any point. It still applies. Then summation of an should be infinity as well. And this is kind of obvious, right? Because if this adds up to infinity and you're adding up something that's bigger than bn, this should be bigger or equal to this one, and therefore this has to be infinity. Does that make sense? Okay? Is that good? See, we have two things. Bn is smaller than an. The smaller ones add up to infinity, and therefore an should be bigger than this one. So this has to be infinity as well. Does that make sense? Okay, good. All right. Now, on the other hand, if you have something positive, or at least non-negative, and an is less than bn, and sum of bn converges, then summation of n equals 1 through infinity of an should converge as well. And this time the inequality is the opposite. Bn is bigger than an, so the sum of an's must be less than bn, sum of bn's. But because sum of bn converges, this means that it's a finite value, right? And you have something positive that's less than some finite value, so that means this has to converge. Does that make sense? You're adding some positive quantities here. You're only moving right. But I know that somebody ahead of you already went and they couldn't go beyond a certain point. Then this one should also not be able to go beyond that point. So this has to be stopping somewhere before. That's the idea. Is that good? Okay. Yeah, so what I'm really trying to say is that if an is less than bn, then if you add them up, it will still be true, right? So if that's true, then this will be true, and this is some finite number, let's just say c. And sum of positive number cannot go over c. Then what is it? It must converge to some number before c. Yeah. If you're adding positive numbers, you have only two choices. Either it goes to infinity, or it stops at some finite number. And because its upper bound is some finite number, this has to be finite. That's the idea. Okay, so let me try to use this to prove some things converging, diverging. Okay, example 1. Show that sum of 1 over square root of n minus 1, n from 2 to infinity, diverges. Okay. How would you do that? Now, eventually the comparison test will be your least favorite test because you have to figure out some inequality. Inequalities are harder than equalities. A lot of the other tests, you just simply have to compute something and the computation tells you whether it converges or not. This one, on the other hand, you have to find something that's bigger or find something that's lesser. So, because you want to show it diverges, which one are we trying to use?
The top one.
The top one. This one is the one we want to use. Which means I have to find something that's less, but then when you add them up, it diverges. Okay? And here's a principle that we'll be using many, many times. If you decrease the denominator, what happens to the fraction?
Bigger.
Becomes bigger. If you increase the denominator, what happens to the fraction?
It's smaller.
Gets smaller, right? And because I want something that's smaller, do I want to increase the denominator or decrease the denominator? Increase the denominator. Okay, so here's the question. Is there something that has bigger denominator that looks simpler?
Could you square the whole thing?
No.
1 over
So-
square root of n.
Tell me, what did you say?
1 over square root of n.
Yes, just simply 1 over square root of n. Right? See, this itself is bigger than this. So as fractions, this fraction will be smaller than this one. But at the same time, summation of 1 over square root of n is summation of 1 over n to the 1/2 power. So by the p-test with p equals to 1/2, this what? Diverges, converges. This will be diverging. Will be infinity, right? So that means by, or we can say so, by comparison test, this, or summation of n equals to 2 to infinity of 1 over square root of n minus 2 minus 1 diverges. Now let me show you this second example. Second example is the other case. You want to make it smaller than something else that converges. Example 2. N equals to 1 through infinity of 1 over n times 2 to the n. Does this converge or diverge? And often this is the way the question will be given. It will not tell you whether you have to prove it converges or you have to prove it diverges. So that's why it becomes important that you have some intuition behind whether this is going to converge or diverge. So what's your feeling? Would this summation converge or diverge? What makes you think that?
Because this infinity, it's 1 over infinity.
Yeah.
2 to infinity would be there.
So 1 over infinity is 0,
Yeah.
but that's the limit of the sequence. We're talking about the sum of those, right?
Oh.
Don't confuse between the sum of the sequences, don't confuse between the limit of the series and the limit of the sequence. It's very confusing, and we have to use both. But make sure that you distinguish between them, okay? So the individual terms go to 0. That's good, because if it didn't, then we know it diverges right away. So what makes you think this diverges? No idea. What makes you think it converges?
Well, the
Can't
sums
you-
go to infinity?
The first rule you have for the p test,
Yeah, it's equal.
n is going to keep getting bigger, so p is always going to be greater than 1, so it will converge, won't it? Or it's gonna
I
keep-
don't really understand your reasoning.
Well, because the exponent n is going to
Oh,
keep
okay,
getting
okay.
bigger.
So you're kind of thinking n to be like p. Okay, okay. Yeah, but that's not the right analogy.
Okay.
Because this is n times 2 to the n. N doesn't go here. But think about it this way. When n is like 10, 2 to the 10th power is about 1,000. And you have 10 times 1,000 is like 10,000.
Because
You have 1 over 10,000. Compared to like 1 over n squared. So compare that with, say, 1 over n squared. Which one's faster? Which one's going to 0 faster? This one going to 0 faster, or this one going to 0 faster?
The
that
top
one.
one.
That one, right? If you plug in 10, it's like 1 over 100. If you plug in 10 here, it's 1 over 10,000. So the things that you're adding here is going to 0 much faster than this one, but even this one converges, right? Does that make sense? But although it's actually true that this will be always less than this thing, it's not so easy to prove that. So instead, you have to try to come up with something else. But at least we know that we're trying to show that this converges. Okay? To show it converges, I have to say this thing is less than something. And hopefully that thing on the right side converges when you add them up.
Can you just do 1 over 2 to the n?
Good idea. Okay. Actually, you really have two choices, right? You have, and the reason that these choices work is because if you decrease the denominator, then the fraction increases, right? See, n times 2 to the n is definitely bigger than just 2 to the n, right? Because n is like 1, 2, 3, 4, 5. If you delete that, this denominator is smaller. But if the denominator is smaller, the entire fraction is bigger, right? Same deal here. 2 to the n is bigger than 1. So if you get rid of it, you get a smaller denominator. Therefore, the fraction will become bigger. However, among these two choices, this is a bad choice because what's the summation of 1 over n?
Oh, it diverges.
It diverges. It's infinity. So showing that this is infinity doesn't tell you anything about this one. Because all it says is, oh, this is less or equal to infinity. Yes.
Would that be technically indeterminate between both of them?
That would be, like, if you use this, it will be, like, indeterminate because, all right, so that's a good point. So if you have, like, if you have a strict inequality and if you add them up, the summation will be like that. And we know that this is infinity. So we know that this is infinity or something smaller. But wait, we already know that, right? If you add positive things, either it will go to infinity or it will be some finite value, right? So this doesn't tell us anything at all. So that's not helpful. So we go back here. If this is true, then we know that summation of n from 1 through infinity of 1 over n times 2 to the n is less or equals to 1 through infinity, 1 over 2 to the n. And now the question is, does this converge? What type of series is this? Huh? No, it's not a p-series.
It's a geometric.
It's a geometric series, right? with R being
1/2.
1/2. And because the common ratio is between 1 and -1, this does converge. By the way, we don't, although we can find out the exact value for this one, we don't want to. We're not interested because that's not going to be really telling us anything about that. Okay. Oh well, it might. We do know that a over 1 minus r. So when n is 1, a is 1/2, r is 1/2. So that's going to give you 1. So we know that the summation of this will be less than 1. So that's something better than not knowing anything. But what's really important is that this converges because it's less than some finite value. If you're adding positive things, there's no way for it to diverge if it's less than some finite value. So we can say now that by comparison test, this converges. And when you plug in 1, it gives you 1 over 2, so it's bigger than 1/2 and the summation is less than 1, so it will be a value between 1/2 and 1. But the exact value is not known. Any questions? Yes.
How did you determine that it does converge just by looking at it in the beginning? You did not know that?
Oh, I'm just saying that this goes to 0 very, very fast. And that's some intuition. Or if you don't have the intuition, what you can do is you can try to prove both. Try to see what can be done. And if you try to show that this diverges, you're going to fail because it's a converging series. Yes?
So when we chose the 1 over n and we compared it, it didn't help us, but that just doesn't, then we could just switch to the other one?
Yeah, we just switched the other one and it helped us.
What happens if they both don't help?
Then you have to find something else. That's why it's tricky. You have to be creative in figuring out what to compare with. So the comparison test is the trickiest one to use. Therefore, I'm teaching you this, but try to use some other tests.